Hello and welcome to a buildingSMART webinar. This webinar is part of the buildingSMART Virtual Summit for Spring 2022. Thank you for joining. My name is Dan Little and I will be your moderator today. Today's webinar is titled Infrastructure Room 2 Part B, IFC Tunnel. And we have an expert panel. This is the second session. The first was yesterday. Our speakers today will be Michel, André, Borrmann, and Sergej Muhič. This webinar is scheduled to last an hour with a chance for questions. The webinar is being recorded and will be made available in the replay section of the event within 24 hours. Before I hand over to our speakers, I would like to remind you that your phone lines will remain muted for the duration of this webinar. If you have any questions or wish to make comments, please use the chat box in the control panel on the right-hand side of your screen. I would also like to bring to your attention that buildingSMART is committed to ensuring that participation in the development of standards is unrestricted, and the process for their adoption is transparent, and standards that are developed do not favour any particular provider and are open, non-binding and accessible to all. Please take note of our antitrust code of conduct on the screen. And with that, I would like to pass the floor to our speakers. Opening words from Michel.
Hello, everybody. Thank you very much for joining us today. This second expert panel on behalf of the IFC Tunnel team is very much on the extensions that we would like to propose for advanced geometries, dealing with the way to modelize properly the non-linear transition in between cross-sections, the way to represent different subsoil conditions which are non-continuous through 3D grids voxels, and the way to link with external data that is potentially stored in other formats. André will be with this team developing these concepts to you for review and for opinions. I've not been long with buildingSMART International, but I have to say I come to realize how knowledgeable and experienced this technical team of ours is. It's been really an impressive set of information that this team has to deal with, and a very interesting exercise they had to go through with three different domain teams providing requirements, and there, of course, the need to understand what those domain experts were requesting in order to make the proper choices when it comes to the different options on how to implement those requirements into the IFC mechanics. So frankly, I think that without this terrific expertise, we would not have been in a capacity to be so quick with providing this implementation we are proposing to you just yesterday and today. With that, André, I hand over to you for this expert panel.
Yeah, thank you, Michel. Hello, everyone. My name is André Borrmann. I'm professor at the Technical University of Munich, and I have the pleasure to be the technical lead in the IFC Tunnel project. As Michel already said, we had a quite big expert panel yesterday already, where all our domain experts presented in detail all the developments in the different fields of tunneling. Today we will dive a little bit deeper with respect to fundamental extensions to the IFC standard to cover things like alignment, georeferencing, geometries, and so on. So first of all, let's have a look again on the development process so that everyone understands how it works in general. We started with the requirements analysis. We had domain taxonomy definition, both of which was done by our domain experts. We take this as input to come up with the conceptual model, which is modeled using Enterprise Architect in UML. This conceptual model is then used as basis to create the actual schema extension. This is part of the work that we are doing as IFC experts in this project. we first come up with a draft version, which is then used for validation. And then, of course, after validation, we will have a final proposal for the IFC extension. And then hopefully we will get also formal approval from the bodies of buildingSMART International. So in more detail, from a technical point of view, this is the workflow that we follow. As I said, we had developed the requirements analysis report already back in 2020. On this basis, we have extensive taxonomy spreadsheets developed by the domain experts. This was all covered yesterday. Next to that, we also have, of course, requirements that address more fundamental things, like, for example, georeferencing and geometries. Nevertheless, we use this input for creating the UML model that we see here in the middle. We use the UML modeling guidelines that have been developed by the Rives team and the IFC Infra room. This continues to be very useful. So we come up with this UML model in Enterprise Architect. From this, we can create UML reports. We will see some of the snippets of these reports today. But in the end, after finishing the conceptual model, we will also publish the final UML report. This is then used as input for the developments in IFC Doc. This is the tool that we use for creating the actual schema extension. Everything we do there is open, documented in Github, so everyone can see what we are proposing there, can provide his or her comments, and create alternative proposals. So when this is done, then we create the actual schema, both in Express as well as in XSD, and also the HTML documentation. The entire process will be done a couple of times because, of course, we will have to get feedback, we will have to do tests and so on. So we have to do this in an iterative manner. Let's have a short look on the requirements analysis report. As I said, this was published already in 2020, July 2020, where we listed use cases, processes, data exchange scenarios. But also, and this is important for us today, we addressed these fundamental aspects that are necessary to create proper tunnel models, including georeferencing, alignment, geometry, and spatial structure. And these are the 4 aspects that we cover today here in this session. Next to that, we also, as I said, had a very detailed description of domain-specific items, object types from geotechnics, systems, evacuation, structures, and lining. But this was all covered yesterday. So today we will essentially focus on this part here. As I said, we use UML for the conceptual model. We make use also of the modeling guidelines that have been produced. Essentially, we use UML models, first of all, to capture all domain-specific requirements. You see this as so-called virtual entities in the diagrams. So these are not IFC entities, but then in the next step, we map these virtual entities on either existing elements in IFC or new elements that we are proposing as extension of the existing standard. The next step then is the actual schema extension, as I said before. This is completely done through GitHub. In the background, we use IFC Doc, but everyone can really see what we propose there, can follow our discussions, can create new issues if he or she wants, and also create own proposals for extensions with respect to covering these different aspects. So that's completely open. Everyone is invited. Whoever wants to join us there can use these links to see the current stage of development. Yeah, now let's jump into more specific aspects. And the first specific aspect is geodetic coordinate reference systems. And to this end, I hand over to Sergej. Sergej, please.
Thank you. So my name is Sergej Muhič. I will be presenting a couple of these technical discussions parts of our ongoing work. One of them being the geodetic, or let's say the georeferencing part. We have engaged quite a few experts on this. We're quite proud that we also have some experts from the geodetic domain, even supporting us, especially for clarifying the new entities, the new definitions, and also for coming up with proper templates, which will be the second part of our work. But for now, we're just focusing on the actual firm definitions, how these then go together, because obviously IFC allows entities to be combined in various ways, will then be completed in templates. We have started a quite good discussion also on GitHub regarding this, because our pull request system allows really granular changes and really granular discussions. And I will be presenting also this part a bit. So first of all, what are the requirements? The obvious first requirement is that tunnels can be quite long objects, and that means that we quite quickly come into limitations if we're using Cartesian coordinate systems or local coordinate systems for that matter, due to the curvature of the Earth, obviously. And that means that the coordinates of geometry still have to be somehow converted. They have to be used in the proper way, and there's no real option to use only local coordinates due to the length of the facility. So for this, the good thing is that our geodetic domain colleagues have developed all kinds of coordinate operations, transformations, and have built up quite a substantial knowledge of how to deal with the Earth's curvature. And the good thing also is that we can tap into this knowledge to define our concepts. So what this means is that each and every coordinate has to be represented on the Earth's curvature, and that means that one of the axes or two of the axes are not really straight. They're not they do not define a plane. They do define a surface, but it's not a plane. So what we can then do is we can project these to a plane to have a Cartesian way of dealing with stuff. But that also means that the entire geometry is distorted. It's not really flat and will not look the way it looks if we just took the coordinates from the distorted values. It will not look the same. And this is kind of our first requirement, and IFC had no way of dealing with all the possible representations until IFC Tunnel picked this up. There was a map conversion, but mostly it was not used in the right way, and there was no proper certification. So there's that, and we kind of picked it up. So maybe we go to the next slide. What we came up with is this proposal. In the end, such a complex matter has been dealt with quite elegantly, I would say, with two new entities and one potentially new entity that could even be replaced by a simple attribute. So there's still these two alternatives that we're looking at, and we also have a schema that was generated for both alternatives. as you can see in the slide here, that's the well-known text representation, and this well-known text representation will also give us the ability to get rid of ambiguous attributes such as scale and map conversion. So the first entity that was introduced is a geographic CRS. As I said, the IFC specification, IFC4 specification, had no way of dealing with this, or it had an old way from IFC 2x3 where latitude and longitude were saved on the IFC site. That's of course quite problematic because it's not dealt with in a proper manner in that it's consistent with what's done with map conversion. So for this purpose, we kind of introduced the IFC geographic CRS, which features geodetic datum, and of course it defines a prime meridian, which is in our case usually the Greenwich meridian, and also defines a unit that's used in this geographic CRS. There's also a couple of wear rules that we already had to define on these entities, such as, for example, the unit is a plane angle in our geographic CRS. Going to the other one is an IFC rigid operation, which allows us to still use georeferencing, but this rigid operation is kind of for the purpose where we use georeferencing just to position something, and we don't take distortion into account. It means that we just move the origin, the coordinate system origin, to a certain point that's georeferenced, and this point just takes our context and specifies our coordinate system at this point, which is then further down the road. It's just a local coordinate system, so no distortion involved. This entity kind of introduces the coordinates, obviously, which are important to locate this point. And the third is the height. The third attribute is the height to have the proper point defined in 3D. A couple of, one wear rule again has to be applied here. This wear rule specifies that our coordinate type is either length measure or positive plane angle measure, and that it's consistent across the board for first and second coordinate. So there's no mixing of plane angle measures and length measures. And this can be applied to both a geographic CRS and to a mapped conversion or mapped coordinate system in kind, as it allows both conversions to be dealt with through length measure and plane angle measure. The third addition or modification here is the introduction of the well-known text, either attribute or coordinate system. What well-known text does is it gives us the ability to encode coordinate systems, not only coordinate systems, but in our case, coordinate systems in a standardized string format, so that in cases where there's no clear internationally agreed code for it, like EPSG, for example, is one option, that a user-defined coordinate system can be conveyed, and it also deals with scale at every point in this in the context of this coordinate system. Basically, gives us the ability to transform any coordinate according to an agreed set of rules. And if we go to the next slide, here we can see the conceptual model and how it fits into the existing schema. You can see that both coordinate reference system and map conversion are supposed to be modified, meaning in the coordinate reference system we would either add this well-known text attribute that I just spoke about, and in map conversion the scale attributes would be removed if we added this attribute. The red outlined entities are the new entities, where the IFC well-known text CRS is the one that might be replaced just with the attribute. The problem with adding this attribute on IFC coordinate reference system is that it kind of somewhat breaks backwards compatibility, because the serialization changes due to a direct attribute being introduced. It shifts the entire set of attributes or attribute values in an IFC step file to the right, one space to the right. So this is something that still has to be agreed on, and also has to be agreed on in the broader community, that this is okay. We're confident that we can go with this nicer method instead of introducing a completely new entity, because it takes into consideration the inheritance of that's built into the IFC model, and it just introduces a much nicer way of dealing with coordinate reference systems, due to well-known text then being available on both IFC geographic CRS and on IFC projected CRS. So we're quite confident that this is the way that we will go in the end, and there will be no IFC well-known text CRS introduced. And with that, I think I can hand over to you, André.
One remark on that. So it's really necessary that we have a very unambiguous definition at this place, because the worst thing that can happen is that we will have really planning and design errors due to a misinterpretation of the fact whether the model is a distorted model or an undistorted model. And in long tunnels, we definitely will have distorted models quite often, which is not so much the case for buildings. So this is really a place where this is absolutely necessary to take attention. Let's jump to the next topic, alignment. So the background here is that, of course, in tunneling, alignment plays a super important role. We have on the one hand side the tunnel axis itself, but also this axis is the basis for all kinds of sweep operations to create the shape of the tunnel in 3D. Also, we use the tunnel axis quite intensively for positioning elements along the axis. So all this has to be covered because these are strong requirements. It's very important to differentiate between the alignment of the roadway and the railway on the one hand side. So we have this here in red on this slide. But then we also have the boring axis. So the as designed axis, where the boring machine is going to be guided along. And then we have the actual as built tunnel axis, which typically has a slight deviation from the as designed boring axis. We had an intense analysis of what is there in IFC 4.3, because IFC 4.3 has really a strong development in the field of alignment, and we could see that it definitely fulfills all the requirements that we have also in tunneling. So we don't need to extend anything there or change anything. So this is perfectly fine. So with this, we jump over to the next topic, which is geometry representations. And again, I hand over to Sergej, please.
Okay. In the geometry representation requirements, we had some specific requirements in IFC Tunnel, especially in the sweep department. So that fits into IFC quite nicely, as if we look at the IFC geometric resources, we kind of have two basic types that we're dealing with. One is, of course, procedural, and the other is explicit geometry, where the explicit geometry would be something like boundary representations, triangulated sets, and so on. And procedural would be something like an extrusion, a sweep of a profile along certain directrix. So we kind of immediately know where we are trying to add on. That's procedural geometry. Other entities in explicit geometry were already quite substantially debated in the previous projects, such as overall architecture, which introduced the IFC triangulated irregular network, and of course there's other entities such as polygonal and triangulated facets there available. Obviously, we also have hybrid descriptions. And there's also the CSG part that we can take use of or use in our definitions. But the one that I was talking about before, we go to the next slide, is something like a guided sweep, where we don't just define one profile and extrude it along a directrix, but we have, first of all, many profiles. That's one requirement, but this requirement was kind of also already addressed in the IFC Road project. But here in IFC Tunnel, since we're not extruding just a section along, we're also trying to describe the shape between two sections. This is what we envision. So a sweep that's guided by a set of curves. It's also kind of a requirement for IFC Bridge, but IFC Bridge at the time deemed that part out of scope and just settled on a directrix. So a section solid horizontal, which basically just introduced one directrix with a set of profiles, and we have kind of added this requirement, having guiding curves between profiles, so that we can describe these profiles. I mean, these sweeps also in between sections. There's not just linear interpolation available. Now we can actually describe these transitions between profiles. So if we go to the next slide, we will see what is currently being discussed, what is currently submitted as a pull request, and of course everybody welcome to chime in on this. We haven't had that much engagement with the guided sweeps yet, as we had with georeferencing. But to introduce this in a bit of a more concentrated manner, how we fit this into the IFC schema is that we introduced a guided sweep that's sort of different from a section solid, in that a guided sweep requires guiding curves. So this IFC guided sweep is being introduced as an abstract supertype of many guided sweeps to come. We'll see. Maybe we just have one in the end, but we kind of set this in place where it can be expanded in the future. This this entity introduces a directrix and guiding curves. This is the main idea that we envision for such a guided sweep, that it has a directrix, a main line or a main curve on according that's being used for the sweep, and we introduce guiding curves that guide the points of the profile along this directrix. Typically, you would see the directrix and the guiding curves being interdependent, so the guiding curves being somehow dependent on the directrix, and that's where definitions from the IFC 4.3 come in with the gradient curve, the IFC segmented reference curve that were introduced then. We also introduced already some restrictions where we restrict the directrix to being a 3D curve, and the guiding curves also. And from this, we then derive the guided sweep solid, which is a solid body model that's constructed based on the guided sweep principles, so having a directrix and guided curves, and then adding a list of cross sections that are positioned along the directrix. So that's the general idea, but of course this has many nuances that I will go into a bit later. But just let me maybe explain the two rules, the two restrictions that we introduced. The size of the cross-section collection and the size of the cross-section positions obviously has to be the same, because we position cross-sections. And we don't allow any longitudinal offsets, because these would just then produce ambiguity into the definition. So each position is always on the curve, and it doesn't. There's no discontinuity on the curves. So let's go to the next slide here. This is a bit of a full diagram. It's kind of an instance diagram, and here we kind of see also the problems that come up with such a definition if we don't actually position the points of the profiles on the directrix. Because now we have profiles positioned on the directrix, which are in a local coordinate system, and then we have the curves that are positioned on the directrix. And this means that the Cartesian points in the profiles do not necessarily correspond precisely with the points that are positioned on the directrix. So this is there's a bit of a mismatch there, and we have a bit of a problem that has to be resolved. But I think we can do that in the deployment phase quite nicely, and you can also see the structure of how this entity is supposed to work. So the guided sweep solid will then connect the guiding curves, which are based on the directrix. It would connect those guiding curves with the profiles and the directrix, where the directrix is our IFC alignment geometry that's typically defined by an IFC gradient curve. That's the general idea, and we can then go to the next slide and try to introduce the other big geometric representation that we were looking into, and that was a big requirement actually also for the exchange of data for IFC tunnels, and these are the voxel representations. So what is a voxel representation? It's just basically a set of small equally sized, typically equally sized boxes that are grouped together, so like Legos, and that results in a 3D representation. It also allows each of these little voxels to be individually addressed for any kind of a attachment of data. So let's say diagrams or representations such as here on the right and beneath, you can produce something like that where then the voxels convey these color codings and separate data on a big solid. Let's go to the next slide. The voxel representation now from the requirements is we kind of fitted the voxel representation into as a geometric representation item into the geometry resource. That's the IFC voxel grid that you see here. It might be more prudent to even put an IFC solid model in between, but that's still up for debate a bit. But as we see, the voxel grid pretty much defines just the context, so the size of the grid in X, Y, Z, and then it defines the voxels basically, and the voxels are just a set of booleans, so a true/false value along X, Y, and Z. The size of the grid is predefined, so the size of the voxel is predefined, so we always know its dimensions, and then just run through X, then Y, then Z with Boolean values, where the Boolean values define if a particular grid location is populated with something solid or not. That's the main idea there. And this kind of a representation then, because it's an indexed representation where the voxels as IFC Boolean are defined in a geometric representation, can then be reused by the product to attach data to it. And the whole idea of data being attached to a product was also pretty much abstracted. Lars already mentioned this yesterday as an addition to products, where the product and the product data can be combined, and the product data then uses through being assigned to the grid, uses the same geometric representation, and that means that we have direct access to the actual values or to the actual voxels, which use the same indexation to apply values to the voxels. And this is quite an efficient solution, and because it allows also the checking of data. So whenever a value would be assigned to a voxel that's not present, you could even have a model check doing that for you. This sort of a validation verification on a high level of models for being proper data sets. We're also trying to reuse as much as possible the existing relationships to convey this information. And we think we're on a good path here. This might be a bit of a older diagram where we have the assignment of product data not yet specified, but we will be working on that also. So let's go to the next slide. Here we now also see the express representation where the voxels are explained. I kind of already touched on this, that we don't use a three-dimensional list. We just use one list because it's typically more efficient to just use one list in various programming languages. And since we have a fixed size with X, Y, and Z being fixed in size, we can easily identify how these booleans, or to which grid location these booleans are assigned to. And as you see below, that would kind of be the idea how this is assigned. In an instantiation, we wouldn't have a true false. We could have T and F also. That would be fine, and to make the file size a bit smaller. Okay, so let's go to the data representations. And as you see, these voxel data representations are imagined to be just the base types. So just representing the base types like integer, real, or vector. And these are then connected to a product. And the location of each of these values would be connected by index to the voxel grid. Why we opted to have only the base types, so the simple types represented and not measures, is that we try to keep the extension of the IFC model smaller, meaning that instead of having 130 representations of voxel data, we just have these three, and these three then allow us to set the measure on the base type, on IFC voxel data, in the values type, so that that attribute would then set the measure value for the entire set of the voxel data structures. And this also means that we do not have to encode the strong type of the measure value inside the IFC dataset, which introduces a lot of overhead again, because then every data value would need to have if it's a non-length measure, would have to be an IFC non-length, non-negative length measure through the entire voxel data value. But here you can see a nice representation of how this would work with just real values, where only the real values are then encoded, and the measure value is on the voxel data attribute. The same logic applies for the values. We go first X, then Y, then Z, and that results in only one list having to be encoded. So let's go to the next slide.
So that's me again. So thank you, Sergej. This was the extensions of the geometry. And well, let's say as the tunnel project, we of course are very much aware that we should keep extensions to the geometry kernel as small as possible. But these two geometry representations were really intensively required from the domain experts. So we believe that we have good reason to go for these extensions. Another aspect that is quite well established in IFC is the spatial structure. You all know the spatial structure from buildings, where we have the site, the building part, the stories, and the individual spaces in the building being hierarchically organized. Something like this is also necessary for the tunnels, however, of course, with another structure. So in our requirements analysis, we found out that we need to handle different scales. So we have the large scale representing an entire tunnel, multiple kilometers long, with different sections. And typically these sections could be about, for example, the construction type, like certain parts of the tunnel could be an open tunnel, a cut and cover tunnel, and other parts are then mechanized tunnels. So that would be one option, to have these sections along the tunnel. Then we have a medium scale. This medium scale typically relates to the different rock classes that we have from the geotechnical model. And these different rock classes or soil classes, they require different types of geotechnical support, and thus have a direct impact on the costs of these tunnel projects. And well, our domain experts told us that this is really an important aspect of tunneling and needs to be represented also in the spatial structure. So that would be one option, to have in the longer sections, again, smaller sections representing these different rock classes. And then we have the smallest scale, so to say, where we have in the tunnel the different zones that have different functional means, so to say, like, for example, clearance space, service space, floor space, track space, and so on. And then, well, in this case, something additional comes into play, because here we have different directions of structuring the tunnel. The one direction would be longitudinal, and the other direction is lateral, both of which has to be possible, and has to be it must be possible to combine them, both directions. And this is what we have done. We have created an extension of the spatial structure. Of course, at the highest level, we have the IFC tunnel element, which is a sub-element of IFC facility. You know that recently with IFC 4.3, we introduced IFC railway, IFC marine facility, and IFC road as subtypes of IFC facility. And while mirroring these approaches, now we have also an IFC tunnel. Of course, we have different types of tunnels, and this is reflected by the facility type enumeration. So this is a predefined type. It's not subtypes, but instead we use the predefined type here. We have access tunnel, we have shaft, we have utilities, railway tunnels, road tunnels, pedestrian tunnels, metro tunnels, bicycle tunnels, bypass tunnels, maintenance tunnels, general underground facilities, and we also have the ramp, which is a special tunnel to access a tunnel from the surface. Yeah, and then we have the individual parts. So we have the facility parts, and here we use IFC facility part. At least in the moment, maybe there will be some changes that we use then IFC tunnel part instead, but this is a little bit depending on the final definition in IFC 4.3. In any case, we will have these predefined types that we see here on the right hand side. So these are the tunnel part types. We have the tunnel section, the crossway, we have the ring section, and you would have the portal. So not too many predefined types. Of course, this can always be extended by user-defined types, but we wanted to keep the number of predefined types small. Coming to the kind of small scale aspect that you have seen before, where we have these different zones in a tunnel cross section, we decided to go for IFC spatial zone, not for IFC space, because IFC space is very much related to the concept of rooms in buildings. And we have with the spatial zone a much more flexible concept already available in IFC. So we decided to use this to define these different zones that we find in the cross section of a tunnel, which is, for example, the NRAG gap. We have the installation, we have the invert, the lining, the interior, clearance, compartment, and service. So these are typical zones. We have other zones that have been existing beforehand, like security, fire safety, thermal, ventilation, and so on. So these are existing already now in IFC 4.3, and of course they can be reused and should be reused also for tunnels. Well, there's one more here, reservation. This would be also a new one. Yes, so that's more or less it for the parts that we wanted to discuss here. Let's have a look on the schedule. So our general schedule of the overall project was that we started in 2019 before the pandemic, actually. So we had indeed a couple of live meetings. Then until the summer of 2020, we worked intensively on the requirements analysis, and we produced this requirements analysis report, which is publicly available, so you can have a look on it and read all the details on the aspects that we just presented, like georeferencing, geometry, alignment, and so on. So this was quite intensive. Then we continued with the conceptual model development, both on the domain side, but also on the fundamental side. So we developed these concepts for the voxel structures, for the guided sweeps, and so on. We created the first version of the conceptual model by the end of last year. And now we refined this, and we will create the final version of the conceptual model very soon and publish it very soon. Sorry. Yeah, when we have done so, and actually we already started with the schema development early this year, and we produced the first proposals on GitHub. This will be now continued throughout the year. We hope that we finish this work by late summer, early autumn, so we can present the final candidate standard that we produced as a basis for IFC 4.4, including all the tunnel developments then on the next summit in autumn this year. Afterwards, we assume that there will be a deployment phase where we will take vendors on board. We have them on board already, but then we will really help them and support them to implement the data structures. It might be possible that we have another round of iteration because then if you start implementing, there might be ambiguities that we didn't find beforehand, but then we fix it together with the vendors and come up then with the final standard, I guess, in 23. Yeah, that's it from our side. Thank you very much for listening. There was a question about the slides. We will hand out these slides very soon after this presentation. So thank you.
Thank you, André and Sergej, for your presentations. I'm just having a look in the comments chat now to see if there's anything else that we can come to. There are a few messages from David. Sergej, I can see you've already responded. And another, I'll just bring this one onto the screen here. Do you think IFC external spatial structure element has also some role to perform, since in building domain also covers what is attached to the building above or underground?
Sergej, I would leave it to you.
Yeah, so I've already tried to give some information in chat, but this was already discussed. I must say that external spatial structure element would be deprecated. I'm not sure why until now it wasn't used that much in the definitions, maybe just forgetting about it, honestly, and somehow it stuff like the predefined type external or predefined type birth made it into IFC space, and that made it contaminated in the sense of also covering the external concepts already. So I'm not really sure. I hope we can resolve this at some point and really decide whether IFC space is supposed to be used or external spatial structure element. What would be the proper way there? course, we can go either way anytime. It just should be clear semantically in the documentation of how these concepts are to be used.
Thanks, Sergej. David also agreeing with you there that it would make sense. If anyone else, any other attendees have any other comments or questions, please do post those in the chat now. Otherwise, we'll be bringing this session to a close. We're just a few minutes from the scheduled end time anyway.
And again, everyone is welcome to also have a closer look on all these developments on GitHub, and then provide feedback on GitHub, because then we can directly integrate it into our workflows.
Yep, the links are already in the slides, aren't they?
They are, yes, yes. And maybe I can post it again.
Yeah. Maybe just post it in the chat once again. And one thing I would also encourage everyone to take a look into the in progress section of our project, where you will see. Do you have the link, André, available? Because otherwise, I just have it. I just know.
Yeah, if you have it, then please share it. I would.
So just look at the in progress part of our project on GitHub. You will see we have a couple of pull requests open there. The pull requests are marked with the symbol of a graph with 2 points and another graph being merged into it. They are usually named feature something apart from voxel grid and construction administration. Oh yeah, that's another pull request that we have to do from the official BSI repository. But if you look at the pull requests, you can easily just go into the pull request, comment on any change. We tend to keep the changes small, so at most 4, 5, 6 files will be in there. And with the GitHub features that it structures the files changed in the folder structure, also you will see which entities this belongs to. And of course, anyone welcome to click in, post their comments, and give us some feedback.
Great, thank you both for pointing the attendees in the right direction there. I'm not sure if Michel, are you still with us? Would you like to have any closing remarks for the session before I bring it to a close?
Thanking everyone, of course, for this for this presentation and all the the work that is happening behind the scene. Maybe just a point I'd like to stress is the importance of those extensions, and specifically the ones around projection systems and coordinate systems. It happens quite often that such tunnels link 2 countries, for example, each country having its own coordinate system, its own projection system might be different, and you end up in a situation where you need to have a project-specific coordinate system, and so this would allow this. So that would lift this pain of having to deal with converting in between coordinate systems by defining a project-specific tunnel, project-specific coordinate system, for example. So just to illustrate the use case.
Great, Thank you, Michel. So with that, I think I will now bring this session to a close. No further questions or comments coming through. Thank you once again for your presentations. This is the last of the infrastructure presentations, and please do join us for the closing plenary later this afternoon, European time, if you can. Thank you also for attending, and see you all soon.
Goodbye.
Thank you very much.
Goodbye, everyone.
Goodbye.